One of the difficult things in chemistry and physics is for students to imagine what the shape of a molecule looks like. Anything in 3 dimensions is difficult for students often. So in this lesson, we're going to build balloon models. Start building balloon models of molecules so that students can actually see what the molecules might look like. In particular, what we're looking at are the bonds and lone pairs in those molecules. So today, we're going to be beginning a lot of balloon models. We're going to spend several days doing models of molecules. So far, we've done molecules of just what the hybridized orbitals we might think of them what they look like. Okay, those p orbitals. Well, that's pretty close to the actual shape. Hybridized orbitals, except for lone pairs, really don't look like the set we did. But that's how we think about it in order to figure out how to make the balloon models of molecules, or get the balloon molecule, or the models of molecules, and particularly when we think about molecules and the shape of bonds. That's what the balloons help us do. Okay, they help us to visualize and understand what the actual molecules, bonds, and lone pair regions look like. So what we're going to do is start with the simplest of these things, or at least what I think is the simplest of these things, and that's the molecule we call methane. Okay, so methane is CH4. Now this process that I'm going to show you right now is what you need to have in your notes for every molecule we're making. Well, we'll let you do a little less of it, some of this, but just follow with me. I want you to have figure out the Lewis dot formula for each molecule we're doing. Okay, we're going to do 2 today in class and 1 for homework. We'll do some more on Monday. So you have to have balloons for several days now. Okay, so with methane, then we've got carbon, which has 4 valence electrons, so we have 4 electron dots in our electron dot formula. Hydrogen has 1 electron dot. It only has 1 electron total, so it only got 1 valence electron. We do the sharing arrangement in this class. That's how I teach you to do it anyway. And I make that clear because in some classes they don't go through this sharing arrangement stuff to figure it out. They teach it in a little bit different way and go pretty much straight to the Lewis dots. In fact, this system has some shortcomings. Okay, if you get to really complex molecules in college or college class, sometimes this doesn't work completely. It's a good place to start, but it has some shortcomings. Okay, but it seems to be an easy way for me to teach students how to start thinking about it anyway. And so now we're going to squeeze the electrons together. We get the Lewis dot formula that looks like this. We squeeze the electrons in between the 2 element symbols, and we get this Lewis dot formula for methane. Then I want to do electron dot formulas to show how we hybridize carbon, the central molecule here, in order to get this molecule to do what it does, to be able to bond 4 times with a carbon. Because the original electron dot formula that we did in the previous unit had the electron dot formula. Orbital notation is what I meant. The orbital notation we had in the previous unit looked like this. And this orbital notation doesn't show us how we can bond 4 times. It only shows us how we can bond twice with 2 electrons there. These 2 electrons are pretty well tied up in a full orbital. So what we need to do is to hybridize. And again, I'm doing a kind of a simplified hybridization system with orbital notation. In college, you'll be expected to do it in a different way. But what we're going to do is we're going to take just the number of orbitals we need to hybridize for bonding. Well, if I have all single bonds as I have here, single bonds are all sigma bonds. Okay, single tells you there's 2 electrons in there. Sigma tells you the shape of the bond and where you find it. Sigma bonds, and all sigma bonds always come from hybridized orbitals. So, long story short, we have 4 single bonds. We need 4 hybridized orbitals. So we're hybridizing all 4 of these orbitals for methane. That's how we know that we need 4 hybridized orbitals, because we have 4 single bonds. Single bonds and lone pairs are always going to come from hybridized orbitals. Okay, so if you know how many single bonds and lone pairs you have, you count those up. That's how many hybridized orbitals you need. That's how you figure out what your hybridization is going to be. So we need a sp3 hybridization because that's going to give us 4 hybridized orbitals for 4 single bonds. And so we're going to take This 1s, we're going to leave it alone because it's not in the valence level. It's not involved in bonding. It doesn't change. And the other 4 orbitals, since we have to hybridize all 4 of these, the other 4 we're going to join together like this. And this is called sp3. This is in the second primary level because that's where our S and P's came from. That's what the valence level is. And hybridization only occurs in the valence level. So we're going to use that coefficient 2 to designate the second primary level. Then we take all the valence level electrons and space them out across those orbitals, pairing up if we need to. Okay, so that's the hybridization then. That's how we get this hybridization for carbon. We need 4 bonds, 4 sigma bonds, 4 single bonds, and so we need 4 hybridized orbitals to do that. So this is sp3 hybridization. All right, this is picturing sp3 hybridization. All right, this carbon atom in this molecule in this Lewis dot formula has to be sp3 because I got 4 single bonds. Okay, and now we're going to do the shape of the actual, or get to the shape of the actual molecule. So the central atom, the one we're going to look at as far as it's causing the shape of the molecule to form, is carbon. And I'm kind of sort of putting that in there as where the nucleus is going to be. Before any hybridization occurs, the original molecule, that had this orbital notation here, had an s orbital in the valence level. This 2s is spherical. And the 3 p orbitals were sort of double balloon shapes, we said. So one double balloon set going like this, one double balloon set going like this, and the last double balloon set has to go through the whole thing, up above the paper and down below it. So we need to draw one of these antinodes as if it's coming out toward you, and one antinode as if it's going back behind. Okay? And so that's our unhybridized set of orbitals. From the unhybridized set, then we need to show how we're going to hybridize this into this sp3 set here. sp3 orbitals are all the same. Here I've got p orbitals and s orbitals, 2 different kinds of orbitals, 2 different energy levels actually. S orbital electrons have a lower energy than p sublevel electrons. All these have the same energy that's somewhere in between the s and the p. But that means they also have to have the same shape. So here's our center of the atom. That's the nucleus and the lower level electrons in 1s. And all these are going to change their shape and orientation so they're all exactly the same. And so we're going to get the s orbital into a single balloon shape. Okay? We're going to get the p orbital that's coming out toward you and behind into a single balloon shape. This p orbital here, this green one, it's going to be a single balloon shape. Now this one has to kind of swing out toward you on the paper. It might not look like that here, but that's what's happening. And the last orbital then has to be sort of tucked in behind, like that, in order to show this arrangement. Now, all the angles, if I had a big needle through the center of each of these balloons, the angles for all these, for the axis of those hybridized orbitals would be 109.5 degrees apart. Okay, so that's 3-dimensional. All right, you can't put 109.5 degrees for 4 angles on a single sheet of paper. It's got to be 3-dimensional. So one going up, one going down here to 109.5 degrees. This one swinging up toward you. Okay, and the orange one swinging back behind. Okay, now that's what the orbitals look like. At least that's the way we think about them. They don't actually look like that because I don't think you can actually have it form. It gets complex. Just take my word for it that we're picturing it like that to understand how we get these molecular shapes. Okay? What's going to happen is that we have 4 hydrogens up here. Each of these hybridized orbitals have one electron in them. Each of these hybridized orbitals then can share one electron with a hydrogen so that it is full of electrons, okay? And you can get 2 electrons in there because they're going to have opposite spins, canceling out the normal electromagnetic repulsion of 2 particles that are negatively charged, and electrons are negatively charged. So what's going to happen is the s orbital on the hydrogen is going to join up with, it's going to become one orbital shared between the carbon and the hydrogen. Okay, and that's going to change its shape when that bonding occurs. So from this then we're going to get the shape of the actual bonds when we join it up with a hydrogen. And so this blue orbital here, or the hybridized orbital, becomes that sort of a cigar shape with a hydrogen up here. Okay? And the pink one, oh, okay? So I'm kind of, it's like it's sticking on there. It shouldn't be sticking on there, but I'm kind of running out of space, okay? Separate those in your mind. And the pink one is going to be coming out sort of at this 109.5 degree angle to connect with a hydrogen. This green one over here is going to be coming swinging out toward me. Now I don't expect you guys to, unless you've taken art and you know what perspective means, to necessarily be able to draw things in perspective. But I'm sort of drawing it in perspective. This sort of shows that it's swinging out toward you because it kind of gets bigger on this end. And then the orange one's going to go back behind. So I get some perspective in there anyway. Okay? So that's what the molecule looks like. And that's the first molecule you're going to make with balloons in here. Okay? So you need long balloons. Now, let me give you a little heads up about the long balloons. Today, and for your homework tonight, you're going to be using long balloons to make a certain shape, and it's going to change a little bit how you're going to work with those on Monday. So let me show you a little bit about how you're going to put this shape together today. So we're going to get to some more complex molecules next Monday, the next time we're together. But for today, what we're going to do is a little bit different than what I'm going to show you right now. When we start the more complex molecules, you're going to need to be able to have a little bit of balloon on the end to tie with. So next week, you're going to want to tie a knot in the end and leave yourself a little bit of a tail, if you will, on there to be able to tie this balloon to the next one. Today we don't need this. All right. Today you're simply going to blow this balloon up either all the way to the end or at least squeeze the air up to the end to make a little round ball on the end, which is going to represent those hydrogen balls I showed you in that drawing. So let me show you what that looks like. Well, that didn't work so good, did it? And that's going to happen sometimes. All right, pay attention. So notice I didn't blow this up all the way. You can blow it up all the way, but you don't have to. You can blow it up part of the way and simply squeeze the air out to the end. Okay? So what I want is a little round ball at the end, so I'm going to keep working it like that, and then twist it up and tie it off. And there's the little hydrogen part at the end. Okay? Now then, I need to blow up a bond. Okay? Here's what you need to know, guys. Everything depends on the size of your round balloons. Okay? Can I borrow your model right there for a second? If you have a round balloon of balloons, these round party balloons that blow up this size, then the bonds you make need to be only slightly longer than this, okay? You don't need a 3-foot long bond, all right? You want, if this is, I'd say this is about maybe 7 inches from the knot at the bottom up to the end of the balloon, so maybe you want an 8 or 9 inch bond, okay? Can I borrow yours a minute? Because that's the smaller set I see out here. Oh, no, let me see yours. There we go. That's what I need. Here we go. All right. So here's another model with smaller balloons. Now, if you've got round balloons this size, then your bonds need to be shorter to match the size of your round balloons, okay? All right, so if I were making a bond like this, I'd only have a bond that's about 6 inches long, okay? So just remember that. You don't want really giant, long bonds, all right? You want bonds that are moderately close to the, or slightly larger than the balloon model you had, okay? So let me blow up one that's, well, I don't know, I'll make it 8 or 9 inches here, somewhere in that neighborhood. Okay? And so that's what each of these bonds are going to look like. This is going to be a representation of a sigma bond. You got it? You already know what lone pair balloons look like. Like these, the green one, yellow one, and blue one he has here in this model. Okay? Those are what your lone pairs are going to look like when we get to those. Right now you're just making 4 of these, all different colors, to make a molecule that looks like methane. Okay? So when you're done, you need a balloon model that looks like this. Got it? Now, in addition to what's right there, you need to label some things. These are going to be sigma bonds. Okay? There are 2 electrons in each of those bonds. Okay? And that's the model you're going to make for methane. So do that now, and then we'll move on to other models after that. For the model of methane, if you don't already have it, you need to make sure you have in your notes the formula, the correct Lewis dot formula. If you can do the Lewis dot formula without having to do this first, that's fine for now. The hybridization for the central atom, and then the drawings for how we got to the shape of the molecule. What I want you to do next in class is do a molecule for H2O. And this time I'm not going to show you all those steps. This time I want you to figure it out for yourself. All right? That's the class activity. And you're getting, by the way, once you finish these, you need to bring those to me to grade, okay? Make sure they're labeled properly and that sort of thing. The difference with water, between water and the methane molecule, is with water, a little heads up, you're going to have a couple of lone pairs. These are hybridized orbitals like the models we did yesterday and the day before, or the previous time we did sp3. You're going to have hybridized orbitals, but there's nothing in there. So that's round balloons, okay? So for water, just heads up, you need 2 long balloons and 2 round balloons, okay? Now the homework, I'm not going to tell you what balloons to use for the homework. You've got to kind of figure it out. So again, go through all the steps. For the homework, you're going to show the formula. I want to show you the formula. Show me the Lewis dot formula, the hybridization for the central atom, and then how we get to that final model shape, okay? And the homework you're going to be doing is for ammonia. Now guys, like water, everybody knows the formula for water, H2O. Ammonia is a molecule and a formula you need to know the formula for by heart, by memory, okay? It's a common name for a molecule. Doesn't follow the IUPAC rules for naming it. You need to know that NH3 is ammonia, okay? But that's your homework. And when you get done with that, you want to have all those drawings in your notes plus the model. And again, I'll have a document on Google Classroom for you so you can post your pictures if you want to do it that way rather than bring it in here on Monday. You can bring it in on Monday if you want to, okay? And don't wait till Super Bowl night to try and do this, all right? Get it done, kind of early while it's fresh in your mind.